Hello, everybody. Today we're going to be doing problem 6.10 by Griffiths. An iron rod of length L and square cross-section side A is given a uniform longitudinal magnetization M. So we're just going to stop right there. First, we're going to calculate the surface current, the bound surface current. And to do that, we have to remember the formula for how we calculate the bound surface current. And we calculate that by taking big M cross product the n hat. So the order here will matter. So using the right hand rule, stick out your index finger for M, stick out your middle finger towards the direction of n hat. So this is going to be n hat. Why is that n hat? Because that's going to be the normal here. That's going to be n hat. So the M is going that way, the n is going that way. What you're going to get is a vector pointing down, because you have to kind of turn your right hand upside down in order to make that possible. So your thumb is going to be pointing down. So if you think about it, the bound surface current is going to be doing a loop kind of in that direction. So that's the direction that the current is going to go. That's I. Or we could say K bound. So now that we figured out where the bound surface current is, we can continue going. So the next section says, and then bent around into a circle with a narrow gap width W, as shown in figure 6.14. So find the magnetic field at the center of the gap, assuming the width is much smaller than A, and A is much smaller than length. And they're very courteous, or Griffiths is very courteous to give us a hint here that says treat it as a superposition of a complete torus plus a square loop with reversed current. So I was actually reviewing the solution. I did this problem myself. I reviewed the solution on Quizlet, and they gave a completely different, not completely different, but a slightly different answer, because they assumed that this torus right here could be treated as a very long cylinder, pretty much a square cylinder. However, the hint says that we want a complete torus. So actually, that solution may have been incorrect. Now, there's two ways of interpreting it, but it turns out you actually get a different solution if you treat this torus as a very long cylinder. You want to treat it as a complete torus. So if you recall from a section, what was the magnetic field of a torus? Well, the magnetic field is zero everywhere outside the torus. And inside the torus, it looked like U naught K, magnitude K, all over 2 pi times the length from the axis. And it is going to be azimuthal. I'm going to put a little phi hat there. So this is going to be inside the torus. Now this S is important. And that's what kind of changes the answer, is that depending on where you are in the torus, depending where, somewhere along the length here on the axis or on the radial axis, it is going to change the magnetic field just a little bit because of this S right here. So this is why our answer is going to be a little bit different if we treat it as a complete torus instead of a very long cylinder, if we look very close up. Another hint that this problem gave us is that we need to add a square loop. And I'm assuming you thought to add a square loop here. Now, since the current is going this way, we should make an opposite current going that way. So if you view it from this angle, it's going to be counterclockwise. And then from here, it is going to be clockwise. So we're canceling out that clockwise current by creating a square loop with counterclockwise current. Now, what is the magnetic field at the center of a square loop? Well, I'm not going to calculate it here. But it's going to be equal to 2 times the square root of 2 mu naught I all over 2a. And it's going to point outwards. Now, I did write a vector notation here, so I'm just going to say z hat. And I'm going to call z hat, you just treat it outwards like that. You remember the right-hand rule. The vector, or the current is flowing that way. That means the magnetic field is going that way, which will cancel out the magnetic field that's going that way from the surface current. So that's going to be magnetic field at the center of the square loop. And I'm encourage you to calculate that yourself using all the techniques in previous chapters and sections. But now what we're going to do is just simply combine these two. Now here's a little trick. See, we have an iron rod of length L here, but we need to figure out where this S position is. But since W is much smaller than A, which is much smaller than L, we can assume that if we take a very long square cylinder of length L, and we sort of bent this into a shape of a torus, leaving a tiny little gap, a very, very small gap, then wherever we are, because all of these quantities are much smaller than L, that we can just assume we use L, or the inner radius here, instead of some L plus some A over 2. So for example, S of the center here is going to be approximately L divided by 2 pi. So that's all I'm going to say. L divided by 2 pi. That's going to be the S of the center. So this in turn means that our magnetic field, the center here, is going to be, let's see here, L. Because 2 pi is going to cancel out. So we're just going to have divided by L in the phi hat direction. It's going to be in this direction here. Then we have another magnetic field from the square loop here. Remember, we're just adding a square loop. It's going to emulate it having a gap. Center of the square is going to be 2 times the square root of 2 mu naught I over 2a. And it's going to be in the opposite direction. It doesn't really matter what we call the vectors here, called z hat, phi hat. Maybe we can say that this is going to be negative phi hat. All that matters is that when we combine these two fields, that we get the correct answer. So finally, the last thing we're going to do is just simply combine these two. I'm just going to say it's a magnitude, but I'm going to give a direction here. It's just going to be equal to, we're going to take this and we're just going to subtract this quantity. So mu naught over k, L, and then we're going to subtract 2 times the square root of 2 mu naught I over 2a. Now before we factor anything out, what we want to do first is figure out what I is. Now because we're using a square loop here, we're going to try to relate this to the surface current. And the surface current, or relating I relative to the surface current, is going to be approximately width times whatever the current is. So because we're subtracting, we're taking the opposite current. We're just going to take the magnitude of the surface current. We're going to say I is approximately the width times the surface current. So you can imagine, instead of having a thin wire, we have a very thin rectangular square loop with some width. Because remember, we're trying to cancel this tiny little section out by putting an equivalent square loop on it. So all of this is approximation. The problem first thought this. That's why they said that W is much smaller than A, which is much smaller than L. So after simplification, should get mu naught k 1 over L 2 times the square root mu naught I. Oops, not mu naught I, but W all over 2a. That's going to be the final answer.